So let me try.
Maybe
Did you give me permission or?
I think you should be able to share. They're saying that you are a co-host. So
Yes, okay. Now where should I go to share?
I think there's this green
Okay,
button at the bottom.
probably you will see my screen,
Yeah, I
but
think
this
it's
is,
coming on. Yeah.
can you see it?
Yeah, it's good. Can you do full screen maybe? Or it's already full screen?
It should be full screen.
I think it's okay. Yeah.
Okay.
It's clear enough. I think it's fine.
Yeah, on my screen, it's full screen. So, so you tell me when I should start, huh?
Is there a way to make the volume up or not?
Uh,
No, sorry. Huh? Yeah, can you increase the volume, please?
Not on my side, or
No. Yeah, the IT people. I'm just talking to the IT.
okay,
Sorry.
okay,
They'll increase the volume in the room.
okay.
Okay. Okay, great. So, yeah, maybe we can start.
Good afternoon, everyone, and welcome to today's ICTS string seminar. We are pleased to have Marc Henneaux giving an online seminar. He will tell us about the Wheeler-DeWitt equation in asymptotically flat spaces. So over to you.
Okay, well, thank you very much, and thank you very much for the invitation. So it will be indeed a pleasure to talk about the Wheeler-DeWitt equation in asymptotically flat spaces. So what is that? So, well, the Wheeler-DeWitt equation is in fact a long history, and it was very popular in the 80s because it plays a central role in the canonical approach to quantum gravity. If you formulate gravity in Hamiltonian form, then you are immediately led by applying Dirac prescriptions to the Wheeler-DeWitt equation. Now, probably the success of string theory has a bit made the Wheeler-DeWitt equation less popular, but in the recent years, it has been the object of revived interest, and mostly in the asymptotically ADS context. And I believe that one of the reasons for this revived interest is that it raises questions about non-perturbative quantum gravity that actually any theory of gravity will have to answer. Now, in particular, and this was actually one of the motivations for my recent work on that, was this very intriguing connection pointed out by and explored by Raju and collaborators, that the Wheeler-DeWitt equation, in fact, captures already holography because of its non-local character in space. Now, as I said, although there were work in that context on the asymptotically flat context, mostly the ADS situation was the one investigated. And in order to extend that analysis to asymptotically flat spaces, one needs to have a better control of the infrared structure of gravity when the cosmological constant is zero. Now, the infrared properties of gravity in the case of lambda equal to 0 are very different from the ones when lambda is strictly negative, and they are different in many respects. One, I'm working here in 4 dimensions, is that the asymptotic symmetric group of asymptotically flat gravity is infinite dimensional. It's a famous Bondi-Metzner-Sachs group, while in the anti-de Sitter case, it would be the anti-de Sitter group, which is finite dimensional in 4 dimensions. Now, connected with that, and as pointed out by Strominger, the vacuum in asymptotically flat spaces is not unique, but it's infinitely degenerate. And another property that these vacua are not isolated in energy from the other states. While in anti-de Sitter space, we think that the vacuum there is a gap with the other states. And so if we want to make progress on understanding and extending previous results to the asymptotically flat case, we need to really understand better how the BMS group would act on solutions of the Wheeler-DeWitt equation. And this is really the question I will address in this talk, which is based on a recent paper. So I will first briefly review what the Wheeler-DeWitt equation is. I will then explain how the BMS group can be seen at spatial infinity and how it acts on the Wheeler-DeWitt equation, so which will be really based on the Hamiltonian formulation of gravity that originates to Dirac and Arnowitt, Deser, and Misner ADM. But I will show that even though the BMS group was originally derived at null infinity, it does have a description at spatial infinity, which is good if you want to understand how it acts on the Wheeler-DeWitt equation. Then I will argue that really the proper treatment of physical questions, physical scalar products, how to compute expectation values of physical observables, that really the proper formalism is the BRST formalism that I will briefly review. I will describe how the BMS charges and the BMS group element are represented in the BRST formalism and act on physical states, how to compute physical transition amplitudes. And that will be the content of my talk. I should say from the outset that I will mostly focus on the general framework and questions of principles rather than computing explicitly some matrix elements or some other properties of the Wheeler-DeWitt solutions. Okay, so what is the Wheeler-DeWitt equation? Well, the Wheeler-DeWitt equation arises naturally when you follow the Hamiltonian approach to gravity. Well, we know that gravity being a gauge theory, there will be constraints, and which are first class because they will generate the gauge transformations. And according to Dirac, we have to impose in the quantum theory these constraints as operator equation, as conditions on the physical states. And if you do that in the case of gravity, you will get the Wheeler-DeWitt equation. So it will express that if you take an arbitrary combination of the constraints, which I have denoted H for the Hamiltonian constraint, Hk for the momentum constraint, and you sandwich that with an arbitrary vector field that goes to 0 at infinity, that gives you an operator. That operator should annihilate in the physical states. So what are H and Hk? They are the quantum versions of the Hamiltonian and momentum constraint functions, which I have written here. And what is psi perp and psi k? This is an arbitrary vector field, but it is required to vanish at infinity because it should describe what we call a proper gauge transformation. What is a proper gauge transformation? It's a gauge transformation which does not change the physical state of the system. Well, that's why the state should be invariant under the action of the corresponding generators. So it really corresponds to a redundancy in the description of the system. While if psi perp and psi k, as I will discuss at length in the next slides, if they don't vanish at infinity, they will describe physical transformations that do have an effect on the physical states. So I will call the transformations that go to 0 at infinity and have no effect proper gauge transformations, and the other ones I will call improper gauge transformations. Okay, so in the expression, I don't know if you can see my mouse. Can you see it?
Yes.
Yes, okay. So here H is the Hamiltonian constraint. It's a quadratic expression in the momenta conjugate to the metric. So capital Gij-Mn is the so-called DeWitt supermetric, here it's, or the inverse rather, here it's expression. Pi ij are the conjugate momenta to the metric, and Gij is a spatial metric. Everything is three-dimensional here, so spatial. And this is the spatial covariant divergence of the conjugate momenta. Now, the Wheeler-DeWitt equation is really obtained by expressing that the physical states should be annihilated by the constraints. It was originally written in the metric representation. So we have the Q's and we have the P's. The Q's are Gij, the P's are the momenta conjugate to Gij. So we consider the state of the quantum gravitational field as functional of the metric. That was what Wheeler and DeWitt did. And then the conjugate momenta would be functional derivative with respect to the metric with h bar over I. And if you substitute that in the quantum constraints, you get the second order functional differential equations with respect to the metric, which are clearly non-local because they connect points at different points on the same slice, and rather complicated to be solved indeed. And to be given meaning too, in fact, but I will remain at a rather formal conceptual aspect. I will assume that we have been able to give a meaning to these equations. Well, they are complicated because here you are taking second order functional derivatives at the same spatial point, and we know that there are divergences. But I will not talk about this in my lecture.
Sorry, Mark, maybe I
Yes.
misheard, but the question, did you say these equations are non-local or?
Well, you see, you have the spatial curvature connects different spatial points. So these are non-local in the sense that they don't reduce to equations, differential equations at each spatial point, but they will connect through the curvature and also the second one, a different spatial point. So you cannot think of psi at x as independent from psi at x prime.
But that is true even in gauge theory, right? Like the
Yes,
divergence.
that's right. That's right. So I'm not saying that from that point of view, it's not something new.
Okay, okay, thanks.
But it's just that, well, also in gauge theory that will be non-linear, so they are complicated. But here they are highly non-linear because you have the inverse metric which appears, and so it's non-polynomial. Okay, but I will not focus on these. There are difficulties, but assume that we control them. Okay, but on top of these, what I would say, although it's difficult to disentangle technical from conceptual, on top of these difficulties, there are conceptual difficulties. And I will really focus on the conceptual ones.
Just by non-local, you just meant the appearance of spatial derivatives.
Exactly. In space, yeah, this is non-locality in space.
Could I just add one comment to that?
Yes.
I think the fact that, so if you integrate these equations, you will find, for instance, that the ADM Hamiltonian is integrated to some integral of some local stress energy density.
Well, let me perhaps talk about the ADM Hamiltonian on the next slide.
Yeah, no, I was just responding to Raghu's point in terms of that's one manifestation, at least in ADS.
Yeah, and we have also something like that here. So, but before, let me go, on the next slide, I will talk about improper gauge transformations and the energy and the BMS generators. But here, let me just point one thing, that the second of these equations is well understood. It just expresses that psi, the physical wave functional, is invariant under diffeomorphisms. So if you change the metric by a diffeomorphism, the state will not change. By a diffeomorphism, I should say that vanish at infinity. And then that means that psi only depends on the three geometry, not on the way you describe the geometry, the coordinates you are using to describe the geometry. And then the first equation become an equation for this functional of the geometry. And sometimes it is that equation which is called the Wheeler-DeWitt equation. But I will use the terminology Wheeler-DeWitt equation for the equations written, on the previous slides, independently of the representation in which you work, whether it's a metric representation or the momentum representation or a mixed representation, which sometimes people are using in asymptotic, are using. Okay. But we know that this is not the whole story. If we have asymptotically flat spaces, we have to supplement the Wheeler-DeWitt equation by, well, actually, there will be more to come, but at least by a Schrödinger-like equation that tells us how the physical states change when you are making an asymptotic time translations. So if you take a vector field that goes to an asymptotically time translation, then the states will change. So it does have an effect on the physical states, and it will change by a Schrödinger-like equation where the Hamiltonian. So this is just to tell you that asymptotically we get something that goes to a time translation of unit length, and where the Hamiltonian will be given by something that we have seen before, namely a combination of the constraints sandwiched with the vector field, but there will be a surface term. And this surface term will contain the metric evaluated at the boundary, but because of the constraints, of course, you cannot think of the metric at the boundary without, because the metric obeys the constraint equation, without, I mean, it is connected with the metric inside. So even though I can write it as a local thing in terms of the metric at the boundary, that thing itself depends on what is inside because of the Hamiltonian constraints. And so actually this was, I believe, one important ingredient in the work by Raju on why the canonical gravity contains information or captures holography. Because the energy, we know, is quite an important operator in any quantum field theory. Okay, but now let's go to BMS. We know that the asymptotic time translations only form a subgroup of the asymptotic symmetry group of gravity in the asymptotically flat context. We can make rotations, we can make spatial translations, we can make boosts, we have the full Poincaré group, but we have even more. The complete asymptotic symmetry group is the BMS group, and it is infinite dimensional. Well, this has been identified in the early 60s of the previous century, and this group is a semi-direct product of the Lorentz, well, talking about the algebra now, so the BMS algebra will be the semi-direct product of the Lorentz algebra by an infinite dimensional abelian subalgebra that contains the translations, and if we had only the translations, time and space translations, that would be the Poincaré algebra. But in addition to the translations, ordinary translations, we have the pure super translations. So that's why we have much more. And we can write ADM-like expression for all the BMS generators, not just the energy as I wrote on the previous slide. That can be worked out. And again, they will be expressed as a linear combination of the constraints. That will be the bulk part, but the constraints on physical states have the zero action, plus a surface term. And the surface term will really be the important thing. And so from that point of view, all the BMS generators, just like the energy, will define boundary observables, because they will be gauge invariant under gauge transformations that vanish at the boundary, as they should. Now, the expressions are in the literature. Here is a reference if you want. But so the structure is, as I said, the following. So if an arbitrary BMS transformation will be prescribed by a vector field, the behavior of which inside is not really important. It's really the asymptotic behavior which is important. I hope I wrote it, yes. This vector field will have to behave asymptotically as an infinitesimal BMS transformation. So more explicitly, it will contain a homogeneous Lorentz part, so a boost part. So beta perp I is a constant that describes the boost transformation. There is a spatial index I because there are three directions in which you can make the boost. Then similarly, we will have a spatial rotation part described by an antisymmetric tensor BKI. Both these homogeneous Lorentz transformations blow up at infinity linearly in R, okay? And then you will have transformations which are of order 1 at infinity, which contain the ordinary transformations, but also the super translations. And they are described by these functions T and W. So T and W are just functions of the angle. So they are of order 1 in R as you go to infinity. And then there will be subleading terms, but the subleading terms are not very important because they define proper gauge transformations. They will not contribute to the surface integrals. Okay, now this is the Hamiltonian description of the BMS super translations. We know that at null infinity, we have a single function of the angles. Here we seem to have two functions of the angle, but they have definite parities. T is an even function of on the sphere, W is an odd function on the sphere, and you can combine them. Well, it's not just the sum, but in a more complicated way to make the connection with the super translations at null infinity. But so we have the same number of an arbitrary function on the sphere, one arbitrary function on the sphere with no definite parity. It is split naturally in this way in the Hamiltonian formulation. But this, in a sense, is a technical detail. But so these are the super translations, and they are parameterized by functions on the sphere, so they will contain all the spherical harmonics, T only the even spherical harmonics, and the zero spherical harmonics, the constant, will just correspond to time translations. W will contain all the odd spherical harmonics, and the first spherical harmonics, if you compute this, will just give you spatial translations. But they are higher order harmonics, and these describe the pure super translations. Now, we see that all these transformations are accompanied by surface terms. So these are surface terms. Mu nu and beta are surface terms. Mu nu would be the angular momentum and the boost generators or center of mass generators. So they are connected with these constant beta perp I and beta ki. But all the surface term in beta, in this curly b, is the surface term associated with BMS transformations, which will contain in particular the the ADM energy when you take for T a constant and W 0, but it will contain much more. So also, well, I will write the expression for B in a second, but before writing the expression for B, note that when the constraints hold, H are equal to 0, HK equal to 0, the bulk term is equal to 0, everything reduces to the surface integral. So in that sense, we do get boundary expressions or boundary operators in the quantum theory. Now, what are the expressions for the super translations? For the charges, here they are, but maybe I should not spend too much time on that. So they will be clearly proportional to the parameter of the transformation, T and W, and they will actually feel the deviation from Minkowski, well, just like the ADM mass. So for the super translation in time, you will have the first order deviation of the metric from one is for first order. That will be a term of 1 over r in the metric expansion from Minkowski is contributing. And for the momenta, well, the momenta starts at order 1 over r squared. So it is 0 for Minkowski, and then the next term will be 1 over r squared. And it is the coefficient of that 1 over r squared term that will appear in the expression for the spatial super translations. In particular, linear translations would have, so linear momentum would correspond to taking for W the first spherical harmonics. And that would reduce to expressions given by ADM. But you have more. We have more because T is an arbitrary even function on the sphere and W an arbitrary odd function on the sphere. Now note that for Minkowski, all the surface integrals are 0. I adjusted, in fact, the surface integrals to be 0 for Minkowski, but otherwise they will be different from 0. Now, yes?
In the case where we work in Bondi gauge, then this is all just Bondi mass aspect integrated with different spherical harmonics. Would that be right?
Okay, then you can indeed make the connection. Well, so I'm here on Cauchy hypersurfaces. So you need to make it's a good question to say, oh, how do these quantities connect with the expressions at null infinity obtained in Bondi gauge, for instance? And they do connect. You can show that they are the same in the limit that you take, in the past limit of future null infinity or in the future limit of past null infinity. So if you take the Bondi mass expression, for instance, and take the limit u goes to minus infinity, it will connect with the ADM mass. That was well known. But if you look now at the other super translation generators, they will also connect. You can prove that, indeed.
Think of these as being strictly evaluated at spatial infinity.
This is, yes, I am on you see, all the Wheeler-DeWitt equation formalism deals with Cauchy hypersurfaces, and the metric Gij is of Euclidean signature. Okay, so these are Cauchy, so indeed, so, and this is spatial infinity, and that's why they are of course strictly conserved.
Slightly
Okay.
tangential to what you're saying. Is there any advantage to trying to blow up spatial infinity, or is it just fine to work in some large R formalism and not worry about trying to resolve?
Well, it is, well, of course, I'm not giving all the details here, but if you want to make the connection between these expressions evaluated at spatial infinity with the null infinity expressions, yes, indeed, a good way to proceed is to blow up spatial infinity, because it's very poorly represented in Penrose, on the Penrose conformal diagram. So one way to do is to use hyperbolic coordinate as introduced by Ashtekar. But I think that if you really want to make the connection controlling all quantities all the way to null infinity, the Friedrich coordinates, which were introduced by Helmut Friedrich, are the best. So indeed, if you want to make, of course, you might say, I don't care about null infinity, but that would not be, I think, a good attitude. You could say, well, I just remain on Cauchy hypersurfaces. It's a complete description of the system, but I think it's not the most useful one in many questions. If you want to make the connection, then there is a definite advantage in connecting. But I will not talk about that here. But that's discussed in the references I gave. Now, let's go to the quantum theory. So I will assume that I have been able to define the operator so that the first class property is maintained, that the Wheeler-DeWitt equation has been given sense. And then because of the first class property, because of the fact that these BMS operators are gauge invariant, they will clearly map solutions of the Wheeler-DeWitt equations on solution of the Wheeler-DeWitt equations, because they will commute with the constraints. And then that means that we expect to have the BMS group to have a unitary action. But then you ask, what does unitarity mean? And more generally, should I compute scalar products of two solutions of the Wheeler-DeWitt equations? And then more generally even, how should I compute expectation values of gauge invariant between two solutions, such as BMS generators, which are gauge invariant operators? And why is it a non-trivial question? Because you might say, well, I just compute the scalar product. For instance, I work in the metric representation, and I define it by a functional integral over the metric of psi star Gij, chi Gij. But we do expect...
Excuse me. So these asymptotic symmetry generators can have commutation relations between them, right?
Yes, so there are two things to be distinct. It's a non-abelian algebra. For instance, they transform under asymptotic Lorentz transformations non-trivially. They form a representation of the homogeneous Lorentz group, indeed. But these are improper gauge symmetry. So when I talk about gauge invariance, I mean commuting with the generators of proper gauge symmetries with vector fields that vanish at infinity. And with these generators, they do commute, exactly.
And so, sorry, could you show the expression for the generators again?
Here, this one?
But these ones are all improper, right? Because you have some expression.
Yes, yes. So these ones form a non-trivial algebra, but that's fine.
Okay.
What is important is that they do commute with the generators, okay, this one, where psi perp and psi k goes to 0. In that case, there is no surface integral.
Okay.
And then they do commute with these ones. This you can show, because the constraints are first class, in fact. Is that
okay? Thank you.
fine? Okay, so let me continue. So as I said, the naive scalar product will diverge. Why does it diverge? Because you are, I mean, the way the Wheeler-DeWitt equation expresses gauge invariance. And so when you will integrate over the gauge direction, because the functional do not depend on the gauge, you are going to introduce infinity. Well, this is a classic, a well-known typical problem of gauge symmetries. gauge theories. So, and I think that the best way to, and so I have to tell you how to compute physical amplitudes. Now, you might say, well, let's just put a gauge condition and not integrate overall gauge degrees of freedom, which are in physical. But then you have the question, what happens if I choose the gauge differently? Am I sure I will get the same scalar products? And I think that the BRST method, and that's what I'm going to explain now, is the most powerful method for achieving the task of computing scalar products which have, between physical states, which have a well-defined significance independent of the gauge or the, yes. Okay.
So, hello, I had a
Yes.
question. So,
Yes.
before we go to the quantum theory, in the classical theory, is it obvious how the symplectic structure and all work, taking all these things into account? Like, is the symplectic, the Poisson bracket, is it clear?
Yes, so I will assume that I indeed I will apply, but this is what Wheeler-DeWitt did, namely that Gij is like Q from the point of view of the symplectic structure, pi ij is like P, and so we do, we take wave functions that depend, that's one way, wave functions nulls that depend on the metric, and because of the symplectic structure, we know that the conjugate momentum will act as different first-order differential operator with respect to the corresponding Q. Yes, so from that point of view, this is what we assume. Now,
Yeah.
you might say there might be anomalies in the constraints. Maybe the algebra will not be preserved. These are interesting questions. I will not treat them in this talk because I want to emphasize other questions. I will assume that somehow we have been able to give a meaning to this, and that gauge invariance has been maintained, and that the BMS symmetry is there. And I would like to indicate how to compute in a significant way, gauge independent, by that I mean gauge independent way, a scalar product and physical amplitudes.
Yeah, so maybe this is what you're saying you don't want to talk about, but like what about the boundary conditions on the the symplectic form and so on and so forth? Like,
well, I'm assuming that the fields have some decay at spatial infinity. And so, for instance, in the metric representation, I will only consider configurations of the metric that obey these boundary conditions. Then I have, and then pi ij will, I mean, you can show pi ij will preserve that. Yeah, so I do indeed impose boundary conditions. You are completely right. So should I proceed? Well, maybe the questions will get refined. So let me proceed. Now, a quick survey of the BRST construction. So I will extend the phase space by introducing anti-commuting variables. Now, the recipe is to introduce as many new, as many ghosts. So they will be fermionic, these ones, the ghost and the anti-ghost. So I introduce as many as they are constraints. So I would have ghosts which I call C-perp associated with the Hamiltonian constraint and CK associated with the momentum constraint. They have ghost number 1, anti-commuting. Then there will be the corresponding anti-ghosts, which have ghost number -1. So when there is a bar, it means that the ghost number is -1. That's a nice convention to keep track of the ghost number. And they will have conjugate momenta. I'm working Hamiltonian. And so there will be conjugate momenta to the ghosts, which have ghost number -1. And these are P bar perp, P bar K. And then there will be momenta conjugate to the anti-ghost, PK, P perp, and PK. And then I will also explicitly keep the Lagrange multipliers, the lapse and the shift, which I will denote for reasons that you will understand later, lambda perp and lambda k. And they will have their own conjugate momenta, which I denote B perp and BK, but because they are Lagrange multipliers, they are not true degrees of freedom. The corresponding conjugate momenta are constrained to vanish. In some treatment, they appear as primary constraint, but let's not talk about that. So I will extend my phase space by many new variables, which are all these new variables. the Lagrange multiplier and the momenta have Gauss number 0, and they commute, of course. And then I will assume, because they correspond, they're associated with the proper gauge symmetries, that all these new fields vanish at infinity. And then the recipe is you construct the BRST charge, which is a real quantity or Hermitian when you go to the quantum theory. And the way it is constructed is that you have a piece which is proportional to the constraints multiplied by the ghosts. So that's this piece here. And so if you commute the Poisson bracket of any quantity with omega, you will first get a piece that looks like a gauge transformation because the constraints generate gauge transformations, but where the gauge parameter is replaced by the ghost, C pub Ck. And then, because omega obeys a key property, it is nilpotent of order 2, you need to complete that expression, because the constraints are not abelian, by terms that contain the ghosts and the structure functions of the constraint algebra. And so these terms will be in total cubic in the ghosts. More precisely, they will be quadratic in the ghosts and linear in the conjugate momenta. So in total, that's cubic, 2 plus 1. And these terms are, in a sense, decorate. They follow from that. They are just there to ensure nilpotency. And then you have the part which is connected with the Lagrange multiplier and the corresponding constraints. But these constraints being abelian, it's not particularly complicated. They are just the constraints times the corresponding Gauss number 1 variable, which are really the momenta conjugate to what people call the anti-ghost. So this is omega. Okay, I'm not going to explain more. It's just the recipe. There is a well-known recipe. I give you first-class constraints. There is a general construction of the BRST generator. And in the case of gravity, here it is. Now, again, I will assume, as I said, that the constraints remain first class and that there is no problem, which means that in the quantum theory, in terms of BRST, this classical Poisson bracket relationship, recall that they are fermionic variables, so the Poisson bracket is symmetric. When you go to the quantum theory, it will become the anti-commutator, so twice omega squared. And so in the quantum theory, I'm assuming that this property is preserved, and so I can talk about the quantum cohomology.
Mark, there's
I
a
have
question.
Yes,
Hi,
please.
have you assumed any gauge fixing condition in?
No, that's a good thing. I think that sometimes there is confusion. A very good thing of the BRST formalism, if you follow the lines of Fratkin and Vilkovsky and Batalin and Vilkovsky, it's really the Russian school which has developed that initially, and then it has been expanded, is that you can talk about the BRST charge without talking about the gauge fixing. And this is nice because it clearly indicates that the BRST cohomology that I'm going to define does not depend on the gauge fixing. If you mix from the very beginning gauge fixation and BRST, then you might wonder, oh, but what happens if I change the gauge?
Right.
Here, you can talk about BRST without gauge fixing, and then there is a procedure to fix the gauge, but you are sure that this procedure, because of the very structure of that procedure, will preserve all the nice cohomological properties that I'm going to describe. And so you can talk about the cohomology without ever having to worry about gauge fixing.
Thank you.
Okay. But it's true that many times people do the two together, and then they will say, oh, the BRST symmetry is what remains, is the residual symmetry that remains after gauge fixing. But I guess that this is a bit confusing for the reason that I just explained. Now, what are the observables? Well, the observables in the BRST formulation are the
There was also a question from Joseph Samuel. Maybe you can
Yes.
just unmute and ask online. Sam, are you there?
Please go ahead, but you should unmute yourself. Yes?
Hello, please hear me?
Yes?
Yeah, is it a problem that the constraint algebra has structure functions rather than structure constants, as usually happens in gauge theories?
No, it's not. You see, that's another very good thing of the BRST formalism, as developed by the Russian school and further developed by others later, is that it applies to all theories, whether the constraints form a Lie algebra in the strict sense or not. So it will apply, actually, that was the main motivation. It will also apply to supergravity, where not only do you have structure functions instead of structure constants, but the algebra only close on shell. And then you will have more ghost terms in the structure of omega, but there are theorems that show that it always exists, and so it's not a problem from that point of view. It can be a technical complication, but the concepts are the same. You will always end up with a BRST charge that is nilpotent.
Thank you.
Okay. Okay, so indeed, in the case of gravity, formulated in the Hamiltonian formalism, you don't have true structure constants because there are some redefinitions. You have structure functions, but the BRST charge for gravity is the one I wrote on the previous slide, and it is indeed nilpotent. Okay, so the BRST cohomology defines the observables at ghost number 0, and so in particular, the generators of the BMS symmetry will have BRST extensions. You see the nice thing also of the connection between the BRST invariant operator corresponding to a given gauge invariant operator is that when you set all the ghosts equal to 0, it will reduce to it. But it's decorated by ghost terms, which guarantees that it will commute exactly with the BRST charge. So in particular, the generators of BMS symmetry, which are observables, will have BRST extensions, which have ghost number 0. And well, I just wrote them, but I'm not going to spend too much time explaining how you get them. The important thing is that if you set the ghost equal to 0, and let me write this. All the ghosts are hidden in delta perp and delta k. So as you can see, these are terms involving quadratic in the ghost. They have ghost number 0, but they contain something of ghost number -1, something of ghost number 1. So, okay, they are here. You see that if you set the ghost equal to 0, you recover the generator of the BMS symmetry that I wrote previously, namely a linear combination of the constraints in the bulk and then the surface terms. And the surface terms are not changed because the ghosts go to 0 at infinity. They describe proper gauge symmetries. Okay? But there are extra terms which have to be included proportional to the ghost because you want this equal to 0 exactly. So you want the BRST extension to indeed correspond to something which commute with the BRST generator. Okay, but again, there are general theorems and there is a recipe for constructing this decoration. In a sense, this is a decoration which is added so that this holds. Okay, so there is nothing really deep in that because there is a general theorem telling us that they always exist.
Mark, could you please explain what is the meaning of BRST extension again? I didn't quite get it.
Okay, the BRST extension is the element in the ghost numbers, is the ghost number operator corresponding to the classical observable. So for each classical observable, you can define an element in the BRST cohomology. That means that you can define a ghost number operator, if I am quantum, which commute with the BRST charge. Now, why do we call it BRST extension? Because it will defer that thing which commutes with omega, if you can see my mouse, okay, will differ from the original classical observable, okay, without the ghost, by ghost terms in such a way that if you set these ghost terms equal to 0, so if you set delta perp equal to 0, delta k equal to 0, it will reduce to the original observable. And so because it reduces when you set the ghost equal to 0, we call it a BRST extension. You are adding ghost terms in such a way that it is BRST closed, that it commutes with the BRST generator. So this is the term. But so what you have to keep in mind is that give me a physical quantity, a gauge invariant quantity, I can always add ghost term in such a way that it will commute with the BRST charge. And conversely, if you give me something that commutes with the BRST charge, set the ghost equal to 0, you will get a gauge. The thing that remains, does not depend on the ghost, will be gauge invariant. Now, what is also important is that two different extensions, there is some freedom in extending in such a way that this is fulfilled. Two different extensions will differ by a BRST exact term. So the commutator of the BRST charge with something. And so in cohomology, it will define the same object.
Are you talking about the cohomologies at different ghost numbers, or?
Here, ghost number 0. For the observables, it's ghost number 0. There might be other interesting things at ghost number 1, anomalies, for instance, or co-cycles at ghost number 2. I'm not going to talk about that here.
Hello. So
yes.
So this delta pup and delta k. So is there a way I can understand it as just the stress tensors of some ghost Lagrangian, or?
Yeah, that's a way to do. And indeed, you might say, oh, now I know how the ghost will transform under the original symmetry, here on the BMS symmetry. So the only, yes, I think you can understand it that way. I'm not, from the point of view that I'm going to develop here, I'm not going to use that, but one way you might say, oh, how do the ghosts transform under the BMS transformation? Well, you just take the commutator with the corresponding generator and you will read the transformation. And so from that point of view, they will be connected indeed with the energy density of the ghosts.
Mm-hmm. So, but there's no like, is this a statement that I've been checked that I can derive it from the Lagrangian point of view and this Hamiltonian point of view?
Yeah, but you see, okay, there is a theorem that comes later that how do you derive it from the Lagrangian point of view? You have to fix the gauge first. And I'm really developing the formalism without fixing the gauge. So I think this is more intrinsic. Now you might say, nevertheless, let me fix the gauge and do it Lagrangian. How does it compare? Well, then there is a theorem that the cohomology gauge fixed, BRST cohomology in a gauge fixed formulation will coincide with the BRST cohomology that I'm describing to you here. So there are theorems indeed, but somehow I'm not using that here because on purpose, I don't want to fix the gauge.
Okay, thanks.
Because, then it's clear that what I'm doing is gauge independent. Okay, so that's for BMS. Now you might say, but wait a minute, BMS, I only describe it asymptotically, but I have a lot of freedom precisely because I have not fixed the gauge in the choice of xi-perp and xi-k inside in the bulk. I give you the asymptotic behavior, but there are many vector fields that will have this asymptotic behavior. So what does that imply? What is this translation in terms of BRST concept? Well, first of all, I should say that because of the non-trivial behavior for a BMS transformation of the corresponding vector field, you cannot write it, these generators that I wrote, it's not exact. But nevertheless, it's close to being exact. In a way, I will precise. If you take two different continuations of the bulk of vector fields which have the same asymptotics, which is the question I was raising, well, then that means that if you go back here, you would have the same surface term because you have the same asymptotics, but you have in the bulk different vector fields. You might say, how do the corresponding BRST invariant objects differ? Well, you can show that they differ by an exact term. So that's what I wrote. So if two vector fields have the same asymptotics, which is what I mean by this symbol, then the corresponding generators will differ by an exact term. And so in cohomology, they define the same thing. And so if you come with a gauge fixing condition and say, oh, I only will use vector fields that obey some harmonic gauge or some, if you prefer something else, some other gauge condition, well, fine, you will get some different P, but they will be in the same cohomological class. But it's very important that this term, because of the surface itself, because of the surface term and the non-trivial behavior of the vector field, cannot be written as an exact term. That would be a catastrophe, of course, but that's because it's a relevant generator corresponding to impropagate symmetry, it does change the physical states of the system. Now, what about physical states? How are they described in the BRST formalism? Yeah, I think I'm probably slightly going over time. I don't know when I should stop. Well, you scream. So physical states are defined by, again, BRST cohomology, but for the state, so they should be
Just
annihilated.
note on the time. Hello.
Sorry?
We typically go over by half an hour or so. So that's
Oh,
okay.
I see.
Your time.
I see. So I should not hurry.
Yeah.
And questions are included, which is
Exactly.
maybe there will be questions at the end, which is fine as well. But it's
Yeah.
good that you interrupt me when you have questions,
So, please
especially
don't
since
rush.
I'm not in front of you. Very good. Okay, so I should not feel stressed by time too much, at least. Okay, thank you. So what about the physical state? Well, the physical state should be annihilated by the BRST charge, and two states which differ by an exact state, namely a state of the form omega acting on something, should be identified, and they should also be at ghost number 0. So the conditions defining physical states are these ones. This is the identification, and you should impose ghost number 0 on psi. Now, actually, it turns out that if you only impose that, there is still some redundancy in the description of the system. It worked very well for the operator cohomology, but for the state cohomology, it's more complicated. You need to impose something extra. All the conditions that I know that you impose extra lead to, in the end, equivalent descriptions, but so you would have many times the equivalent description. So in order to have only one single description, I will impose additional conditions. And the most convenient one, and you will see immediately why, is that I will impose that the physical states be also annihilated by the ghost. It's consistent with the BRST condition. So I will assume that, well, there are the maximally filled states in terms of the ghost. You can view the ghost as, well, we can view psi, the states, as being functions of the ghosts, but the ghosts are anti-commuting. So there will be one state that contains all the ghosts, such that if you add one more ghost, or if you multiply by C1, for instance, it will already contain C1. C1 squared is equal to 0, so it will be annihilated. So this state is sometimes, and I think Ed Witten used that notation, is a maximally filled state. So I will impose that condition on the ghost dependence. But the dependence, if I work in the metric representation and in the representation where the Lagrange multipliers are diagonal, so the rest of the dependence will be functionals of the metric and of the Lagrange multipliers, but the ghost dependence is fixed by that. And well, why is it a useful thing to do? I will now explain. Well, if you impose a BRST invariance condition, so maybe, well, I should have rewritten the BRST invariant operator here, but recall that the BRST, let me quickly flash back the BRST operator. Well, you see that it contains a piece which is proportional to the ghost. And so when I act on a state which is annihilated by the ghost, that piece will disappear, will automatically give 0. It does not give anything. The only non-trivial part, is that, and similarly here, this is quadratic in the ghost. So when I act, even no matter how you define the order, it doesn't matter. There will always be at least one ghost. When it will act on the state which is maximally filled, it will give 0. So that part, omega min, clearly annihilates the state that I wrote. So the BRST condition that the state should be annihilated by the BRST charge will be non-trivial only concerning this, because this is a momentum conjugate to the anti-ghost. We have the maximally filled state in terms of the anti-ghost. So that is going to remove one anti-ghost, so it's not going to annihilate the state. So that will have a non-trivial action, but this is the momentum conjugate to the Lagrange multiplier, should annihilate the state. So that means that the state should not depend on the Lagrange multiplier. So this is what I explained here. I wrote here. Yeah, I should say one more thing, that because these have anti-ghost number 1 and these have anti-ghost number -1, psi, I mean, this is a condition which is compatible with ghost number 0 for psi. It contains as many anti-ghost number 1 variables as anti-ghost number -1 variables. So it has ghost number 0. So the BRST in various conditions just tell me should not depend on lambda if I work in the lambda representation, the Q representation for lambda. But the dependence on the metric, and this is what is, let's say, quite nice, is absolutely unrestricted, because the part that contains H and HK, as I explained, will automatically annihilate the maximally filled state, because the ghosts annihilate the maximally filled state. So any state of that form, where 0 is a state which does not depend on lambda, so the eigenvalue 0 for the corresponding conjugate momentum, will be a solution of the BRST condition. I will call the BRST condition the Wheeler-DeWitt BRST equation, because that's the Wheeler-DeWitt expression. I mean, that's a BRST expression, sorry, of the Wheeler-DeWitt equation. And so that's very interesting that we are able to solve the BRST condition without having to solve the Wheeler-DeWitt equation in that representation. And that's one of the reasons why this representation is interesting. Now you might say, but wait a minute, I mean, we cannot lose the Wheeler-DeWitt equation. How do we have the Wheeler-DeWitt equation in this context? Well, recall that we have to work the cohomology. The cohomology means that I have to identify two states that would differ by an exact state, by something which is omega acting on something. And you can show that you recover the Wheeler-DeWitt equation through that equivalence relation. So to solve the closedness condition that the state should be annihilated by omega is very easy. Here it is a general solution. To take into account the equivalence relationship is more subtle. But okay, that's something that can be dealt with later. At least we can work with physical states. We have to make sure that all our answer or our computations will be independent of that redundancy. This I will discuss now. And then if we want to isolate the redundancy, well, that would be in a sense some gate fixing, but I will not do that, at least not immediately. Now.
I could ask, without
Yes?
introducing the BRST formalism, we could say this is like working with the space of co-invariance rather than the space of invariance. Is that fair?
It corresponds, indeed. You can show that this maximally filled space would somehow correspond to the co-invariance. But the problem with co-invariance and invariance, well, very usually they are defined when you have a group action. It's more subtle to define these concepts when you don't have a true group or true Lie algebra, while here we don't care about that. It's more general in that sense. But indeed, I will make a comment on that. You would recover the analog of gauge a group average when you talk about BRST expectation value. So from that point of view, yes, you are right. But I think it's more general for the reasons I stated. Okay. But the good thing is that at this stage, we don't have to solve the Wheeler-DeWitt equation, which was this complicated equation I wrote at the beginning. Now, let's talk about the scalar product, which is really the important thing. Now, if you naively compute the scalar product, you will find infinity. So let's take two solutions of the Wheeler-DeWitt two solutions of that type. I have to integrate over the ghosts. I have to integrate over the Lagrange multiplier when I compute the scale. I have to integrate over all the Q's. And the Q's that I have chosen in here are the original Dij, but also the lambda mu, the Lagrange multipliers, and also the ghost and anti-ghost, C mu and C bar mu. So I will have a contribution from the ghost and anti-ghost. I will have a contribution from the Lagrange multiplier, and then I have some integral over the metric, okay? But I'm saying that the contribution coming from the ghost and anti-ghost and the contribution coming from the Lagrange multiplier is ill-defined. Why? Because the scalar product of the maximally filled state with themselves, the state contains all the ghosts. So when I integrate over the ghost, we know that well, or if I take two such states, actually the product will be zero. So I will get a zero when from the gauge sector. But then when I integrate over the Lagrange multiplier, which run from minus infinity to plus infinity, it's non-compact, I will get infinity. So really the scalar product, naive, will be of the form 0 times infinity. So it's not good. Now, one way to regularize this scalar product using the ideas of the BRST formalism is to insert an operator that differ from the unit operator by BRST exact terms. So I will define a regularized scalar product as the naive, so this is the expression for the naive scalar product, but with an insertion of this operator. Now, why operator of this type? Well, because first of all, I can choose, as I will show, a k in such a way that the scalar product now becomes well defined, that this ambiguity of 0 times infinity, which I described, is actually resolved. But furthermore, because of this very specific form, if I take another k, which fulfills the condition that the scalar product is well defined, and there are such k's as I will show, because two such k will lead to operators that differ by BRST exact operators, and because these are BRST closed terms, they will yield the same scalar product. So the regularization will not depend on which specific choice of k I take, provided I take k so that it's well defined, and so two such k that can be connected by a line in functional space, such that on each point the scalar product is well defined, it's guaranteed by the properties of the BRST formalism that they will give me the same scalar product. So this is the way I will regularize the scalar product.
Can I ask a question, please?
Yes, please.
So is this choice of K related to the choice of gauge fixing in the Lagrangian formulation of the theory?
It is of the same, in the same spirit. It's different here because we are not trying to fix trajectories. We are really trying to, but it's in the same spirit. And in the Lagrangian formalism, indeed, you will have to choose a k, which is of the same type, but there will be also time derivatives in the Lagrange. For instance, suppose you say I want to work in the Lorentz gauge. The Lorentz gauge contains the time derivatives of A0. Here we are Hamiltonian, so there is no time derivative, and we are working phase space. But in a sense, it is the same spirit, and it's the same type of theorems that hold that there is independence on the choice of k, as well, because the gauge fixing is done in a similar way, indeed. So it's similar in spirit. It's not exactly the same because we are not working in exactly the same spaces.
Right. Thank you.
Okay.
So I'm going to ask a
So,
Can I ask you a question?
yes, please.
Yeah. Hi, Marc.
Hi again.
You keep on mentioning that you can fix a gauge. Now, my understanding is that it's very difficult to really fix a gauge except in very exceptional circumstances, which I know in ADS spacetimes.
Okay, let me come to the next slice where I give you a k. Now, but it's true that when I say fix the gauge, it's actually more, for instance, you might say, oh, but if there is a Gribov ambiguity, what do you do? Are you killed? Well, it's really much more general when I should not use the expression fix the gauge, in fact. I should say I want to choose a k so that this scalar product is well defined. It might be that it will not correspond to a strict gauge fixing in the sense that I will still integrate over configurations which are related by a gauge transformation. That's fine. It might even be more general that, there is some Gaussian average over various gauge and so on. It might be even more general than that. And I will show you an example here where I can write something which is at least formally devoid of this Gribov problem, even though very likely for gravity there are Gribov ambiguities. I don't actually know the full status of that, okay? But I don't have to ask, okay, let me write to you the thing. Because actually we are going to average we are going to make some average rather than fixing the gauge. Okay,
Mark,
Thank you.
related question.
So I think that,
hello?
say, calling K the gauge fixing fermion, as some people do, and actually I do that as well, might be slightly misleading, because you might think that then it's necessary to be able to find good gauge conditions, but it's much more general. Now, there was a question.
Yeah. So at some point you fixed the statement saying that C and C bar annihilate psi, right?
Yes.
So, just related to what you were just saying. So in some sense, probably it's not gauge fixing as such, but in some sense you're maybe choosing some representative in the cohomology, right?
It's slightly more than that, because you could also do something different, which is to say that all the momenta should annihilate the states. So it's a different representation. And in that case, instead of having this description in terms of co-invariant, you would have a description in terms of invariant. So it's more than just fixing the gauge. It's really choosing equivalent descriptions, but not, it's difficult, I think, to relate them by a BRST transformations, because they are different. That's the redundancy I described at the beginning. In the end, you get equivalent descriptions, but it's not completely clear, because you might also have the Gupta-Bleuler description, which is yet another way, which is neither invariant nor co-invariant. Yeah. But maybe I interrupted you too quickly. Your question was longer. I don't know. I'm sorry.
It's okay. Okay. Related question on K, will you impose some condition on K?
I will give you some examples. Okay, yes, the condition is that K should be such that the expression I wrote is well defined. Well defined meaning well defined up to, we are in field theory, this is a complicated, but at least that this problem that I mentioned of 0 times infinity does not exist anymore.
Yeah,
which is a problem clearly related to the fact that we have a redundancy, related to the fact that we are not manipulating gauge invariant quantities.
So for example, would you say that K should be a bulk integral, or is it allowed to also have boundary?
Okay, let me give you an example of K. It will be a bulk integral indeed, because I have to, the problem comes from the bulk in a sense. At the boundary, I have a rigid symmetry. So, and my gauges go to 0 at infinity. So really, it's a bulk problem. So from that point of view, it's a bulk integral. But then I will be able to, let me go ahead. I think that will answer your question.
Okay.
Now, some comment that you can relate it actually to what people do without, in the pre-BRST formalisms, that people have considered what they call projected kernel of gauge invariant operators, where you compute matrix elements of gauge invariant operators between a complete set of solutions of the, in that case, the Wheeler-DeWitt equation. So imagine I am able to find a complete set of the solution of the Wheeler-DeWitt equation, and I'm able to define a physical scalar product among them. So suppose I've done that, which is quite a challenge. Then you could say, then all gauge invariant operators, I can compute matrix elements, and then I can compute the matrix elements in a basis of gauge invariant thing, and I can describe the solution in terms of Gij, and as functionals of Gij and Gij and K, and then you can construct what people call the projected kernel, which is the gauge invariant content of the gauge invariant object. But I will not spend too much time on that, because I can give references if you are interested. But so that's the point, is that it contains all the physical information about physical observables. And you can relate, that's what is interesting, is that you can explicitly relate this BRST expression that I wrote to some concept which are pre-BRST in a sense, but that no one has been able to compute, because no one has been able to produce a complete set of solution of the Wheeler-DeWitt equation in this case. Okay, now, what about K? That was the question. Well, as you see, a very convenient choice of K, which I can do in any gauge theory, is just take the Lagrange multipliers, and they have an abelian gauge invariant. So you see, this is the simple part of the gauge invariant. The gauge transformations act very simply on the gauge, on the Lagrange multipliers, and you take, it has to have Gauss number -1, you multiply them by the momenta conjugate to the Gauss. Then compute that, and you will see that K omega will contain a term that it's proportional to the constraints multiplied by the Lagrange multiplier. So that's nice in a sense, because we recognize the action of the gauge transformations, but then it's decorated by gauge terms, non-trivial gauge terms involving the gauge momenta, and then a term delta mu was quadratic in the gauge. So it's also, there's a gauge here as well, multiplying lambda mu. Now to give some sense of what it does, so if you compute this matrix element of a gauge invariant quantity A, which, so the corresponding BRST invariant operator, you will find that you have to sandwich the states with that, but then you have to compute the scalar product. There will be an integral over lambda mu, the scalar product of the gauge states, and then there will also be something involving the metric. So I'm not writing the integral over the metric, I'm just writing this, okay? And I'm not writing the integral over the gauge, but it's hidden in the scalar product of the upstate with themselves. Now, because of that expression, well, which I have written here, but the important thing things that I want to emphasize is that you have the constraints, which are the generator of gauge transformations, but multiplied by the Lagrange multiplier. Then you have a term that involves the gauge and linear in the Lagrange multiplier and quadratic in the gauge. But then you have a term that involves the gauge momenta. So when you will compute the product of the upstate with themselves, because there is this insertion of the gauge momenta, this problem that I mentioned, that the scalar product is 0 between two up gauge states, is not anymore the case because you have these p that remove gauges. So the gauge scalar product will now be finite. And similarly, the integral over lambda, because things do depend on lambda through that term, actually you will see that you are averaging over the gauge transformations because you are integrating over the Lagrange multiplier, which acts through gauge transformation because you have h mu. And in fact, if I did the same thing for a true Lie algebra, so for an algebra that closes according to a Lie algebra, okay, of constraints closing according to a Lie algebra, you would find that this is exactly the group average. You are integrating over the group element. You have this because that comes from this term. And then you get the R measure, and you get the R measure when you integrate over the gauge. You see, you have this term gives you non-zero, but you have some gauge contribution multiplying lambda, and you will find that lambda is describing the group element. I mean, it's in the Lie algebra, but you have some kind of canonical parameterization of the group. And the function of lambda that you get is precisely the invariant measure on the group, the right-left invariant measure on the group, the R measure. Okay, so this, to connect with co-invariant quantization, this is precisely what captures the BRST formalism, when you choose the states to be annihilated by the ghosts. Okay, but so formally at least, well, of course, these are functional integrals that you have to do. I mean, this is a field theory. It's a formidable task. So I'm not saying that everything is solved, but at least this problem that I mentioned, that the scalar product at a difficulty of being ill-defined, at least formally here, the lambda integral produces an integral over the gauge group, and the ghost integral, which was 0 before, now will produce for you the R measure. Now here it's more complicated because you don't have a true Lie algebra, but the expression would be devoid of the difficulties I mentioned before. Now, if you take in particular for the BMS generators, so you would get the invariant, I mean the physical matrix elements of the BMS operators, okay, which I have written here. And so they are given by exactly the same integral, but you have to insert here P, I mean the BRST extension of the BMS generators. And more interestingly, if you want to look at the group, so insert the exponential, you would have to take the integral of something involving this regularized part time the corresponding gauge invariant object. And recall that this is pure bulk because lambda and the ghost go to 0 at infinity, while here you have a vector field psi, associated with the BMS transformation that asymptotically go to a non-trivial transformation. Now you can combine the two, and again, and that's also multiplied. Recall that this was multiplied by the constraints. This is psi mu times the constraint, and here we have lambda mu times the constraint. So it's tempting to combine the two, which you can do by using the Campbell-Hausdorff formula, or Baker-Campbell-Hausdorff formula. You can combine these two exponential into a single one. And then you will find that instead of integrating over lambda, which fulfills the zero boundary conditions at infinity, you can integrate over n mu that will asymptote psi mu, the one defining the BMS transformation. And so you are integrating, you are making a group average, an average, should not say group average because it's tricky. I mean, we are saying non-trivial in the bulk. You are making an average over all n mu's that asymptotically goes to the given BMS transformation at infinity. And so this is an expression, and then you can see that you have the same non-trivial surface term which appear in the exponential. So you have a piece which contains the constraints. So since I have used a compact notation, otherwise the formulas take the full transparency. But remember, this is proportional to the constraints, and there was some Gauss contribution, but that regularizes the integral over n. And then you find that there is this average because of n. But now n, instead of going to infinity, goes to the asymptotic value, which is captured by the surface integrals. And you have to integrate O over all such n mu's. But so you see that you are not really fixing the gauge, because fixing the gauge would be equivalent to say, oh, once I give you the asymptotic behavior, I know how to continue in the bulk. Actually, here you are integrating over everything in the bulk. You don't fix the gauge. So if there is a difficulty of fixing the gauge, it's not a problem because you don't have to fix the gauge. Now, it's important that, well, you might say, oh, but it looks so much like, if this were a BRST trivial operator, this would really be computing the matrix element of the unit operator. Because it's the same BRST class. But because of the non-trivial asymptotic behavior, this is not a trivial operator, as I explained. And so you get non-trivial matrix elements. And you can show that they reduce to the people had worked out similar matrix element for the Poincaré subgroup, or Poincaré group. And you can show that the BMS expressions that I wrote exactly reproduces these BMS expressions. Now, I think that there is a question.
So this
please go ahead.
Can you hear me?
Yes.
This expression that you showed, where you combine the two exponents to get three terms, is this like you'll get a lot of commutator terms, right? So are they?
There are commutators in the bulk, yes. But the important thing is that these commutators are trivial, in the sense that they can be.
I see.
They can be written as a commutator of omega with something, and because they are trivial, they don't change. That's why I have not written them for that reason. You see.
So they
are sandwiching between physical states.
Are they like proportional to identity?
Yeah. So in a sense, they differ from the identity by something which is trivial. So when you compute with matrix elements between physical states, it's like the identity, indeed. That's why I have not written them, but it's a good question. Yeah, I was a bit fast. Okay, so these are expressions, and actually I will stop here my presentation. So I have been able to arrive at expression for matrix elements of physical observables between physical states, which are, after all, the only thing which are meaningful in a gauge theory. And in particular, I have given expression for the BMS invariant operators, which control the infrared structure of gravity. I have not gone beyond that. In a sense, this is a starting point. You see, because I focused more on the conceptual aspects, but this is really setting the stage for further computation. And I think it was important for me to have expressions, the gauge independence of which were manifest, and this is guaranteed by the BRST method. Okay? And now I think that from these expressions, you can start computing explicit things. For instance, using path integral methods, because it looks like, you are inserting some things like, looks like an evolution operator. So it's very easy to give a path integral expressions of these exponentials. Of course, to compute the path integrals is another story, but you might use perturbation expansions. Actually, you might use perturbation expansions even without rewriting things in terms of path integral. So, of course, this has not been done here. So this is, from that point of view, only the beginning. But at least I think it's important to have a stage in which important conceptual questions, such as how do we control gauge invariance, is proper taken into account. So with this, I will stop and thank you for your attention. So thank you.
Thank you, Marc, for a really nice talk.
Thank you.
I had a question about this. One of the nice things about asymptotically flat space is that we do have a complete description of the Hilbert space, which we get by asymptotic quantization, either on Scri plus or Scri minus. So is there a way where one can show that, let's say one considers a theory of gravity with massless fields, that the Hilbert space and the inner product one gets here would be in precise correspondence with that one gets from asymptotic quantization?
Yeah, that's an interesting question. And I would say that the answer should be ultimately yes. But I think it's something that no one has done. Okay, but so somehow, and maybe this is, we are all familiar with our own formalism. Somehow I know very well the Hamiltonian formalism, and I'm used to work at spatial infinity. But it's clear that there are important questions that are more easily answered at null infinity. And in particular, as you said, there is this construction by Ashtekar of the Hilbert space at null infinity. And clearly we should, it's an important question to connect and hopefully prove equivalence. But because both of them respect gauge independence and respect BMS symmetry, I would expect that they are equivalent, but this has not been proven.
Just to say the connection might be interesting because, of course, there are two Hilbert spaces one gets by doing asymptotic quantization on Scri plus and on Scri minus, and they're not the same. They're related by the S matrix, which is non-trivial. So this might be another description of the Hilbert space that might be unitarily equivalent to both of them, but there might be some interesting relation. It might not be a trivial relation.
I fully agree. I fully agree. And also in particular, I think here you can also ask questions about the S matrix using the old language, like people did in the old days before using null infinity. I mean, by that I mean sandwiching the exponential of the Hamiltonian, and then you take the free Hamiltonian on each side, and you take t goes to infinity and t prime goes to minus infinity. I think that all these should be connected in one way or the other, ultimately. So I agree with you that there is something to, I believe that also that there is something to be learned by doing that. And I think that it will be more than just a direct exercise. I think there will be some non-trivial thing to be understood. Yes, I think that Joseph Samuel has a question.
Can you say a few words about the spatially compact case when there's no asymptotic region and no BMS group? Is that easier or is it harder from either a conceptual or technical point of view?
Okay, so there is one interesting thing. Okay, it's simpler in the sense that you don't have to worry about surface integrals. It's harder because interpretation questions are more complicated. You see, a good thing of having the asymptotic structure is that it gives for you some asymptotic time and some asymptotic structure, which is invariant under Poincaré symmetry and even more, as we have seen. And so you can use all these concepts of flat space decorated by BMS, but still, there is a time, there is some space, and you can talk about rotations, you can talk about boost, an observer living at infinity. In In closed space, you don't have this asymptotic structure. Everything is zero, everything is proper gauge. And now, nevertheless, you can develop a BRST formalism, but I think that the interpretation questions are harder. And people have tried to extract some meaningful time by using, for instance, an extrinsic time or an intrinsic or extrinsic time using the extrinsic curvature. There are theorems, but I think it's more complicated. And also there's a question, suppose I use one time and someone else use another time, how are the things related? I think nevertheless, so I think it's more complicated, but I think nevertheless that again, the BRST method that controls in a very interesting way, I believe, and strong way, gauge independence will still be useful. That's one thing. Another thing that I would like to mention is that in compact spaces, if you are, for instance, perturbing around a background that has isometries, then there are additional complications that we have to take into account. And there are quadratic constraints that we have to take into account even in the linear theory. But okay, but that's in a sense, I would say that it's simpler because there is no surface terms, but more complicated because there is no asymptotic structure that you can use to interpret results.
Thank you.
Could I add a comment on the spatially compact case? At least in the case where we had an asymptotically de Sitter space, we had this set of solutions to the Wheeler-DeWitt equation. And I think there's an interesting question about the inner product. We guessed this inner product, which was mod psi squared integrated over asymptotic metrics divided by volume of diff cross Weil. And that corresponds, I think, in some cases of JT gravity that Sandeep Trivedi and others checked, also to the DeWitt inner product. But it's interesting to ask whether this would be also the same inner product one would get using BRST.
I think so.
This issue of, the fact that the vacuum, the Euclidean vacuum is not normalizable under that inner product. Because when you group average, you need some insertions on top of the Euclidean vacuum. So I think there's an interesting question about the inner product, which would be maybe interesting to understand in this form.
Yeah, so I should separate one thing, that in the de Sitter case, this integral that I wrote will also contain an average over the de Sitter group. But so you will get this thing of, well, I forgot the name.
Inner product. You mean
sorry?
The Higuchi inner product?
Yeah, exactly. You will get that one, which I think is fine. No, is it the one that people want to use, or?
Fine. No, that's fine. Except there's this subtlety that the vacuum is not normalizable under that inner product, because the vacuum gives you infinite norm. The vacuum is, when you group average the vacuum, you get back the vacuum itself. So it's like the problem of defining the string theory partition function, sphere partition function with no insertions. And it would be nice if there's some understanding of that. I mean,
okay, yeah, I agree with you. But okay, but what I can say is precisely you get the Higuchi scalar product. Whatever, I mean, whether it's a good thing or not, I mean, this I don't want to comment on, but this is what you would get. Well, actually, yeah, there is, well, I mean, this would go, we can discuss that. Yeah, I don't want to talk too much about de Sitter here, because that's really not the emphasis I wanted to build in. But I agree, it's an interesting question.
So on some related note, this particular inner product that you have defined, is it clear that it is finite for sensible states like vacuum and so on?
Okay, so it's of course difficult. The difficulty is that we have field theories. So we have infinities coming from the mere fact that we are dealing with field theories. So what you can test is test these ideas on non-trivial theories having gauge freedom, but a finite number of degrees of freedom. And people have tested many models. Actually, there was an interesting paper not long ago by Maxfield and a collaborator on this type of material. And in the case where you have a finite number of degrees of freedom, the problem of getting an infinity due to the integration over the gauge direction is present. The problem of getting zero due to the fact that the ghosts states that we are considering F0 scalar products is present. And so you can see whether you are indeed regularizing. And you can show that when you have a finite number of degrees of freedom, it works well. And you can actually also compare with other representations in which instead of having the maximally filled, you have the maximally empty ghost state, etc., or Gupta-Bleuler. But so from that point of view, it's satisfactory. Now, of course, when you have field theory, I cannot say I can prove it's finite because I have also the difficulties of quantum field theory. And I'm using the Schrödinger representation. So it's a bit tricky as well from that point of view. So that's all I can say.
Okay. A second question. So there is this general, at least statement that is often said, which is that these BMS and so on and so forth are closely related to soft theorems. Now that you have these BMS operators within the BRST formalism, do you see that, like you can use it to kind of derive soft theorems in the BRST invariant way? Or
I would think so. Okay, so yeah, that's one of the goals. What I would do is to consider the S matrix, so which would be related to the exponential of minus I times the Hamiltonian, and which is really the asymptotic the Hamiltonian is the asymptotic time, and I would construct the and I know that it will commute. I mean, when it's decorated with the ghost in a way to preserve BRST invariant, that it will commute with the BRST operator. So there will be some worded entities corresponding to gauge invariant, but we are not interested in that. You really want to see the worded entities associated with global BMS symmetry. But again, you would derive them in the standard way. The S matrix commute with the BMS generators, and so you can proceed. It has not been done, but I think I see no obstacle of principle that it could not be done. But I think that's an interesting question as well, and we can do that in a BRST invariant way.
Yeah, and you could also give a Hamiltonian derivation of the soft theorems. Which,
yeah, I would think, yes. After all, this is the same theory described differently, and in the past, worded entities, well, one way to derive worded entities was more closer connected in a closer way to Cauchy hypersurfaces.
Okay, thanks.
Okay.
So if there are no more questions, then let us thank the speaker once again.
Well, thank you very much.
Thank you. Thanks,
and
Marc.
goodbye, and hello and goodbye to everyone. Ciao.
Ciao.
So it is the end. I leave. Bye bye.
Bye.